Good morning, Antes. Today we're going to look at discrete probability distribution. So remember in the last lesson we looked at what random variables were, and we looked at the expected values of random variables, which are essentially the probabilities of random variables occurring. Alright, so hopefully you've done and been through the exercise on page 119. If you haven't, please consult the memo. There is a memo available on Teams, and you also should have printed the discrete probability distribution student notes, which are also available in Teams. That's what you see in front of you, and that's what we're going to be working from. So if at all possible, and you haven't printed that, please pause the video now, print it. Alternatively, if you have a device where you can work on it electronically and with a stylus or whatever it is, then you can do that as well. It's not ideal just to go through in the textbook, because the research really shows that, especially with stats, if you're actually doing it and filling the things in with me as we go along, you'll retain the information a lot better. Alright, so firstly, there's just a little bit of a recall box there, which just reminds you about what discrete probability distributions are. And you might remember that I told you we're going to be focusing exclusively on discrete distributions as opposed to the continuous distributions in this AP course. Alright, so remember that discrete distributions are ones that take on exact values. So there were no decimals. It was like throwing a coin. You either get heads or tails, not a half. If you're throwing a dice, you either get 1, 2, 3, 4, 5, or 6. And those are the only options, etc. Okay, so down the page, you can see there that we're going to be looking at first binomial distribution. That's what this lesson is. And then next week, when you're back at school physically, we'll be looking at hypergeometric distribution. All right. So binomial distribution. You should know that prefix by now refers to 2. Okay, and in stats, binomial distribution is simply discrete distribution that involves events that only have 2 mutually exclusive outcomes. Remember what mutually exclusive means? Mutually exclusive means that it's either one or the other. All right, and we're going to be calling out of these 2 outcomes, one's going to be a success and the other one is going to be a failure. All right, now it doesn't mean that it's failed as such, but if we're looking, for example, at the probability of throwing a heads when we toss a coin, then the heads would be a success, but the tails would be a failure. All right, because we're looking for the probability of throwing a heads, not of throwing a tail. All right, so let's look at some of the events that we've done in the past exercises that we could use here that are binomial distributed. All right, so the first is tossing a coin. And you know that when you toss a coin, you have only 2 outcomes. It's either heads or it's tails. All right, and then secondly, there can be a soccer game final. Now, why they're saying a soccer final is that in a final, we either have a win or a loss, not a draw. Okay, once there's a draw, then we go into extra time, and if necessary, we go into penalties, but there has to be either a winner, well, there has to be a winner and a loser. All right, and then in a multiple choice test, that's another example of binomial distribution, because in a multiple choice test, you're either wrong or you are right with your answer. Your driver's test, some of you might have already been for a driver's test. Most of you are still going to go at some point, either this year or next year. And in a driver's test, you either pass or you fail. All right, and then rolling a dice. Now, rolling a dice and looking at the numbers is not binomial because there's 6 different options, but we can look at rolling a dice if we're looking at either getting evens or odds on the dice. And that gives us an idea then whether, if we want evens, if we're looking at the probabilities of evens, then if we threw an even on the dice, that would be a success. But if we threw an odd, that would be a failure. Right, over the page, on page 121 of your textbooks, or on your notes on the second page, we're going to look at some of the important properties of a binomial distribution. Now, this is important because when you get a test and you have a question and you need to work out whether the distribution is binomial or hypergeometric, which we're getting to, these are the conditions that you look for that make it binomial. Okay, so firstly, as we've already discussed, there are only two possible outcomes on each trial, either the heads or the tails, the odds and the evens on the dice, or the win and the loss for a soccer final, etc. Okay, secondly, the outcomes are mutually exclusive, all right, meaning if it's heads, it can't be tails, and if it's tails, it can't be heads. Try and imagine a Venn diagram. And on your Venn diagram, if we're looking at the coins, for example, we either have heads or we have tails, and those circles do not interact with each other. They don't intersect. Okay, that's what makes it mutually exclusive. All right, and the third property is that each trial is independent of any other trial. Okay, so remember what that means is if we're looking at the probability of tossing a heads when we toss a coin, and we're not just going to throw the coin once, we're going to throw it 3 times, 6 times, 100 times. All right, now the first time we throw it, we then record whether the coin lands on heads or tails. The second time we throw that coin, the probabilities for a coin are again 50% either way. It doesn't affect the probability at all, whatever the previous toss of the coin resulted in. Okay, so if the first coin was a heads, it doesn't mean that the second is going to be a heads, or it doesn't mean that it's going to be a tails. Okay, the probabilities are independent of one another. All right, and then the last condition or property is that the probability of success and failure remains unchanged at any trial. Okay, because there's no replacement. So remember in those examples of probability when you had like a bag of 6 red marbles and 6 white marbles. Now the probability of taking either a red or a white marble is 50%. If we don't replace what we take, then it affects the probabilities of the next withdrawal. So for example, if we took a white out, then the probabilities of getting a white on the next withdrawal are slightly less because there are now less whites in the bag. Okay, so if that was the case, then this could not be binomial distribution. Right, so in binomial distribution, the probabilities remain unchanged at any trial. Okay, and then there's the Venn diagram that I spoke about, where you can see it's mutually exclusive, the circles don't intersect at all, and these 4 points basically explain the conditions above. Okay, so there are only two outcomes. It can be heads or tails. You can't even have anything out here in the sample space, because when the coin lands, it's either going to land on heads or tails. It can't land on none of them. Heads and tails are mutually exclusive, all right? They don't intersect, and it doesn't matter how many times we toss the coin, the outcome of any given coin toss is not affected by the previous trials. Okay, that makes it independent. And then lastly, the probabilities, as I've explained previously, remain the same every time that we toss the coin. All right, so as I said to you, look at this speech box here, speech bubble. It says learn those properties, all right, because that's how you're going to identify whether a particular problem that you have is binomially distributed or not. All right, and bottom of the page, you'll soon notice that the binomial distribution is an extension of replacement-based tree diagrams. Okay, why replacement-based? Because once you replace the whatever it is that you've chosen, then the probabilities remain unchanged. Okay, so even with the bag and the marbles, that could be binomial if there are only 2 marbles in the bag and one is one color and the other is another color. So if you have a bag with a blue and a red marble, and you pick one out, you record what it is. You might have taken a blue one out, and then you put that blue one back. All right, so that the next time you pick a marble out, there's still one blue and one red marble, so the probabilities remain unchanged. All right, but now why are we going to look at this method instead of a tree diagram is because if you're going to do many trials, even if you do 6 or 7 trials of just tossing a coin, you'll notice that this tree diagram becomes really, really extensive. Okay, in fact, to use a tree diagram for more than 3 trials is already going to be cumbersome. All right, your tree diagram gets exponentially bigger. All right, so let's look at the example on the next page. Okay, before we start example 1, we have 5 examples to get through in this lesson. All right, so once we finish the 5 examples, there will be an exercise for you to complete which you'll actually do next week in class once we've gone through this exercise or gone through the theory together and just consolidated anything that needs to be consolidated. All right, example 1. Thandi is a good goal shooter in netball. The probability that she scores on any given attempt is 70%. Okay, so straight away see here that the probabilities are not 50-50, which they were in all the other examples of binomial distribution that I gave you. All right, so it doesn't have to be 50-50. It doesn't have to be a 1 in 2 chance that you're going to get one or two of the other. Okay, and in this case, if Thandi shoots for goal, it's more likely, in fact 70% more likely, that she will score than that she won't. All right, so it's implied here that if she scores and her probability of scoring is 70%, it's then implied that her probability of not scoring is 30%, all right, because that must add up to 100%. She's either going to score or she's not going to score. All right, so Thandi's practicing and takes some shots at the net. So we're going to look at if she takes 3 shots at the net. Now let's think according to your random variables. Over 3 shots, she's got 4 possibilities. Either she's going to get no shots on goal, or she'll get 1 shot on goal, or she'll get 2 out of the 3 shots on goals. Excuse the hardy-dars. I think they scream because they're afraid of heights. Or she'll score, I said 2 shots out of the 3, or she'll score all 3. Okay, so it's either 0, 1, 2, or 3. All right, so what is the probability A, that she scores exactly 3 times, B exactly 2 times, C exactly 1 time, and D exactly 0 times? All right, so first of all, remember in an exam or a test, we're not going to tell you that this is binomial distribution. So let's keep that on. So we need to first check that this is binomial, okay, by testing it against the 4 conditions or properties of binomial distribution. So the first property, we've got to look at how many outcomes there are. All right, and this is where you're going to fill in. All right, so how many outcomes are there? There's only 2 outcomes. All right, she's either going to score or she's going to miss. All right, so because there are only 2 outcomes, that satisfies binomial distribution. But it's not just enough that that condition satisfies binomial distribution. All 4 have to be satisfied. So let's look at those 2 results of scoring or missing. They are both mutually exclusive. That's the second condition. All right, because why is it mutually exclusive? Because she's either going to score or she's not going to score. There's no middle ground. All right, so that satisfies binomial distribution. Third condition, she takes 3 shots, and each shot she takes is independent, okay, of her previous shots. All right, because if she scores the first one, that doesn't necessarily mean that she's going to score the second one. Okay, and then the last condition is we've got to look at whether the probabilities change or not. All right, so because on any given trial the probability of scoring is 70%, we can then conclude that the probabilities do not change. Okay, so because they don't change, it also means that this is binomial distribution. So because all 4 of these conditions are satisfied, we can then assume that this is binomial. Okay, if you need to go through that again, you can pause now and just go back on the video. Otherwise, let's go on. Okay, so let's look at the information that we know. All right, firstly, we need to know how many trials there are. All right, there are 3 shots. Okay, therefore, n is equal to 3. N represents the number of trials. The random variable is the number of shots that Thandi scores. So if we let x equal number of shots Thandi scores, remember we discussed this earlier, she either is going to score 0 times, 1 time, 2 times, or 3 times. Okay, so that means she could either score 0, 1, 2, or 3 of the shots that she takes. All right, we can call the success outcome score, or S, because they've asked us, if I go back to the question, they've asked us what is the probability that she scores. So because we're looking at the probability that she scores, not the probability that she doesn't score, the probability that she scores will be known as the success outcome. All right, and we're going to use the lowercase p, okay, p for probability, to denote the probability of success. All right, so therefore, the p-value in a decimal form is 0.7 because there's a 70% chance that she's going to score. All right, we can call the failure outcome miss or M, which has a 30% chance. All right, and we're going to use a lowercase q. So we generally use P and Q for these values. Okay, so the Q represents the failure, and therefore in this case the Q is 0.3. So since our outcomes are complementary, remember that because they're complementary, it means it's one or the other, so they both have to add up to 1. 100%. There's a 100% chance that she's either going to score or miss. There's no middle ground. Okay, so it means then that we can make this conclusion that P plus Q must be equal to 1, all right, or 100%. 1 is 100% in decimal form, all right, and that means that Q is equal to 1 minus P. So that is just basically how we worked out this 0.3, all right. Q is equal to 1 minus P, or in this case, Q is equal to 1 minus 0.7, which is equal to 1 minus P. All right. So the parameters that we have, because you need these values to use the formula that I'm going to teach you. Okay, N is equal to 3, P is equal to 0.7, and Q is equal to 0.3. And our random variable, we're just summarizing now, is X is an element of 0, 1, 2, or 3. All right, let's look at the next page. Okay, because this example is only looking at 3 shots, we're going to use a tree diagram just to illustrate it. But remember I said that a tree diagram is quite cumbersome, so don't get into the habit of using tree diagrams for these. In fact, you have to use the formula, which we're going to get to shortly. Okay, but let's understand the tree diagram. All right, so this part represents her first shot on goal, this part represents her second shot on goal, and this part represents her third shot on goal. All right, so she's either going to score with a 70% chance or miss with a 30% chance on her first trial. For her second trial, if she scores, again she has a 70% chance of scoring or a 30% chance of missing. Let's say she missed on her second shot, then she either has a 70% chance of scoring or a 30% chance of missing. Okay, so this tree diagram, I'm not going to read them all to you, but this tree diagram represents all the 8 possibilities of the order in which she can either score or miss. Okay, so the first possible outcome is she scores all 3 times. That's going along the tree diagram on those 3 branches. The second one is if she scores twice, the first 2 times, and then misses. So that's going score, score, miss. And score, miss, score, score, miss, 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 score, score, miss, score, miss, 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 score, and miss, miss, miss. Okay, so those are the 8 different possibilities of her 3 trials. All right, so let's look at A. Question A was, what is the probability that she scores 3 times? All right, so just for now, ignore this handwriting here. We're going to get to that now of Mr. Borken's work. But for now, let's just look at the probabilities here. Okay, so the probability that she scores 3 times is this option. That's the only option. There's only one option. Okay, but how do we get to that? It's 0.7 times 0.7 times 0.7. Okay, so the probability that she scores 3 times is 0.7 times 0.7 times 0.7. Okay, and that we can also represent as 0.7 cubed. All right, and if you work out that 0.7 cubed, you get a 0.343 probability, which essentially means that she's got a 34% chance of scoring all 3 shots. Okay, but we're not worried yet about that value. What we're more worried about is this next line. Okay, because we only got that because of the tree diagram. Now, we're not always going to have a tree diagram, so we have to look at another method of how to do this. All right, out of the 8 ways that have all the different 8 possibilities of how she could score or miss, how many of those 8 ways is it possible for her to score all 3 shots? There's only one way, okay, and it's the first one. All right, so that means there's one way, so 1, Okay, and that represents here that one way. There's only one way that she can score all 3 shots. And we then can multiply that by what is the probability of her scoring all 3 shots? The probability of her scoring all 3 shots is 0.7 cubed. All right, because it's 0.7 times 0.7 times 0.7. And how many has she missed? She's missed 0 of them. Okay, so these two numbers, the 3 and the 0, must add up to the number of trials, in this case 3. Okay, so because she scored 3 times, there's a 3 as the exponent to her success, and she didn't miss at all, so there's a 0 to the exponent of her miss. Okay, if this doesn't make complete sense now, then wait until we get to the end of the example when we look at the probabilities of her scoring either twice out of the 3 times, 1 time, or 0 times. Okay, so we could work out this probability now, and you'll get the same answer as we did in the previous one. It was 0.343. Okay, so that's her total probability of scoring all 3 shots. All right, number B, or letter B, is what is the probability of her scoring exactly 2 shots out of the 3. So we want Tundi to score exactly 2 shots. When I say we want her to score 2 shots, that's what we're working out the probabilities of. Okay, so remember the success is her scoring. All right, so we're looking at the probability of our random variable x equaling 2. Okay, and there are 3 ways that she can score 2 and miss the other one. Okay, SSM, SMS, or MSS. Let's look back at the tree diagram to illustrate that. Okay, so looking at her scoring twice and missing once, there's one option, there's another option, and there's another option. Okay, so there are 3 ways. All right, either she scores twice first and then misses, or she scores, misses, then scores, or she misses and then scores and then scores. All right, so there are 3 ways, as we've just discovered, that she can score twice and miss once. And now we're looking at her 2 shots scored. So remember, the first part of our working out here is how many ways the outcome can happen. Okay, not taking the order into account. Either she scores twice and then misses, or scores, misses, and scores, or she misses and then scores twice. Okay, there are 3 different ways. All right, now we're looking at the 2 shots that she scored. And remember, the success is 0.7 of her scoring. And because she scored 2, we have it to the power of 2. All right, and then how did she miss? She missed 1 shot, and the probability of her missing is 0.3 to the power of that 1 shot. All right, and the odds of that are equals 0.441. All right, so the chances that she's going to score twice and miss once are higher, slightly higher than if she scores all 3 times. Now, that might not make sense to you because the probabilities that she scores are higher, but remember there's 3 different ways that she can score twice and miss once, where there was only one way that she could score all 3 times. All right, let's move on to C. I hope you're starting to get this. But for C, if you go back to the tree diagram, I'm not going to go back now, but we're looking at her scoring exactly 1 of the shots. Okay, so the random probability, our random variable then, is that we're looking for the probability of x equaling 1. Okay, and there are 3 ways that she can score 1 and miss the other 2. You can look at your tree diagram, but they are summarized here. Right, she either scores and then misses twice, or she misses, then scores, then misses, or she misses twice and then scores once. All right, so there are 3 different ways. Okay, so again, 3 ways that this can happen. If she's only scored 1 shot, then we have 0.7 to the power of 1. And if she's missed 2 shots, then we have 0.3 to the power of 2. Okay, and the probability of that happening is 0.189. Okay, significantly less than the probability of her scoring twice, even though there were 3 ways that both of these could have happened, where she either scored twice or missed twice. And the probabilities are now less, because we know that her probability of scoring is higher. So it's more likely for her to score twice and miss once than to score once and miss twice. Okay, so the number of ways is what we need to look at, okay? Because like I've just said to you now that in the tree diagram, we could easily see the number of ways, but if we're not drawing a tree diagram, we need some other method. Okay, so let's look at Pascal's triangle. We have the one at the top here is our 0 row, all right? And that's basically if there were 0 shots, okay? Then if n equals 1, she took 1 shot. Then in that 1 shot, there's one way of scoring and there's one way of not scoring, okay, for each of those 2 shots. Okay, she can either score or she can't score. All right, let's cut down to the 3rd row. So you should remember Pascal's triangle. If we look at the 3rd row, here you can see our coefficients that we had for the number of ways. It was 1, 3, 3, 1. All right, there was one way that she scored all 3. There were 3 ways that she scored twice but missed once. There were 3 ways that she missed twice but scored once. And there was 1 way that she missed all 3 times. Okay, so hopefully you remember your permutations and combinations from last year. Let's look at the 3rd row again, because that's what we've been working with. And I hope you remember this notation here, that we say 3, choose 0. Okay, in other words, scoring 0 out of the 3. All right, so that is one way. So this is when she basically missed all 3 shots. Okay, the second 3 is 3, choose 1. That means scoring 1 out of the 3, and we knew that there were 3 ways. The third one, 3, choose 2, which means scoring 2 out of the 3 ways. And the last one, 3, choose 3, which meant scoring 3 out of the 3 tries, and there was one way to do that. All right, so how do you put this onto your calculator? Right, to put that on your calculator, you're looking for the NCR button. Okay, now the NCR button is just above the divide key on your calculator, so it's a shift button. All right, so in order to type that 3, choose 0, for example, into your calculator, you're going to press the 3 first, then shift divide, and then 0, and then when you press equals, you get 1. Okay, so that represents the one way over here. All right, to do 3, let's do 3, choose 2, for example. You can practice on your calculators to remind you. So 3, shift divide 2, and that gives us 3. So there's the 3 ways in that we can do that. Okay, so what we've done here at the bottom is just to rewrite the answers, but in combination form. Okay, so this part is identical still, but this part is now the combination form. All right, so what's important here is we're going to develop a formula. Okay, so the probability of her scoring 0 times, all right, have a look. How many trials are there? There are 3. Okay, so 3 trials, but she scores 0 times, will always be 3 over 0. Okay, or 3, choose 0. All right, that remains the same. If she scores once, then this represents 3, choose 1. In other words, scoring 1 out of 3 shots. If she scores twice, that's 3, choose 2. And if she scores 3, that's 3, choose 3. Okay, so at the bottom here, we need to develop a formula that helps us remember all of these. Okay, so the probability of her choosing or scoring X times will be 3. Okay, let me just use the other pen. Okay, will be 3, choose X. All right, and in this particular probability, the probability of her scoring remains unchanged at 0,7. And if she's scoring X times, then the exponent here must be X. Okay, so just to help you along, look how this value is always equal to her value of a success. Okay, the bottom of your combination is always equal to the exponent of the success. Alright, then the probability of her missing is 0,3. So remember I told you that these exponents always have to add up to the number of trials. So 0 plus 3 is 3, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 0 is 3. So x plus this must also equal 3. So therefore it's the number of trials minus x as the exponent for 0,3. Okay, so what you have here now is a general formula for this particular example. Okay, why I say this particular example is because the 3, the 0,7 and the 0,3 are unique to this particular example. There were 3 trials. The success of her scoring was 70%, and the failure of her scoring, in other words, her missing, was 30%. Okay? I've already highlighted to you that the sum of the probabilities is always equal to 1. Okay? So the 0,7 plus the 0,3 must be equal to 1. Okay? So that means if we had to add all our probabilities together, because remember they're mutually exclusive, so the probability of x equaling 0, 1, 2, or 3, and the actual probabilities that we worked out is always equal to 1. And this is always the case. Okay, the probabilities must equal 1. Alright, let's expand this formula a bit further now. We know that it's not always going to be 3 shots. Okay, and remember that we use the variable n to denote the number of trials. Okay, in this case, 3 attempts at goal. Alright? So, over the page, now let's assume that Tundi takes n shots. So she could have taken 100 shots, which is almost impossible to represent on a tree diagram. Alright, and it will take you forever. So the formula will then become n over x, because she's scoring x times and she's taking n shots. The exponent for the 0,7 will still be x, because that must be the same as the bottom number over here. And 0,3 is now going to be, the exponent will be the number of shots minus x. Okay, because remember that these values must add up to the number of shots or the number of trials, whatever the context is. Okay, so x plus n minus x will equal n. Okay, so that basically, the sum of those two things that I've highlighted in yellow must equal the number of shots. Okay, so in this case, we know that the probability of success is 0,7, and we know that the probability of failure, which we represent as q, is equal to 1 minus p, which in this case is equal to 0,3. Okay, p being 0,7, so 1 minus 0,7 is 0,3. All right, so now we're going to generalize. All right, we don't always know that the probability of the success will be 0,7%. Okay, so this is the formula now that you need to learn. All right, the probability of the binomial distribution formula. Okay, that's what I'm looking at now in the box here. So the probability that x equals little x, okay, little x, remember, being whatever the success is. So in this case, if she was scoring, that x would represent how many times she scores out of however many trials there are, will be equal to n over x into p into 1 minus p. All right, so remember, n represents the number of trials, p represents the probability of success on each trial, and 1 minus p is the probability of failure on each trial. So this 1 minus p here is basically our q value. All right, and so x, remember, represents the values of the random variables, so either 0, 1, 2, all the way up to n, because now we're not looking at her taking 3 shots. We can work out the probabilities of her taking any amount of shots. Okay, and then don't forget as well, what's not in the formula is that there will be an exponent here of whatever it is. Let me not use a circle because you might think it's 0. Okay, but an exponent of something, depending on how many times she's going to be working. Okay, and that in this case would be x for the p and n minus x for the 1 minus p. All right, as we looked at over here. All right, so as it says, to appreciate the beauty of this formula. Okay, now why is it beautiful? Because if I asked you to do this with a tree diagram, even 6 shots, if you really want to suffer, then take a moment to try and draw a tree diagram with 6 shots. Don't put the probabilities in, but just try and have a look what it looks like. Okay, so this is just an example. Please don't take this down. This is an example to show you of the tree diagram, similar to what we've been doing, but with just 4 trials. And already with 4 trials, there are now, you saw when it was 3 trials, there were 8 different ways. Now with 4 trials, there are 16 different ways, which means for 5 trials, there would be 32 different ways, and for 6 trials, there will be 64 different ways. Okay, really, really ridiculous to draw a tree diagram. Okay, so let's look back at the information that we've been working with. All right, so looking at, as you can see, I've shown you that a tree diagram would be ridiculous here, and I wouldn't want you to even attempt it. But we're looking now if Thandi wants to take 6 shots at the net. Okay, so in other words, our n value is going to be 6. All right, now look in the box. If we use Pascal's triangle, and again, you don't need to learn Pascal's triangle. It's just there to show you what the different lines are in terms of the ways things can happen. Okay, so we're looking at the 6th row now. Remember, the first row is row 0. Okay, so that's row 1, 2, 3, 4, 5, 6. So you can see now that there's 1, 2, 3, 4, 5, 6, 7 different things that are going to happen. Okay, well, 7 different ways that this can happen. All right, so what is on the left here is working out the probabilities for all the different scenarios. So either she scores 0 shots out of 6, 1 shot out of 6, 2 shots out of 6, 3 shots, 4 shots, 5 shots, 6 shots, etc. Okay, I'm not going to go through all these in detail, but I'm going to go through, let's highlight one of them. Okay, so let's highlight this one. The probability of our random variable x equaling 2. And so, using your formula, we know that this part is n over x. So the n is 6 because there's 6 shots. X is 2 because that's what we're looking at the probability of happening. So in other words, her scoring 2 shots out of the 6. Then the probability of her scoring is 70% to the power of 2. Remember, this exponent must be the same as that exponent. And 0,3, the chances of her missing must be to the power of 4 because that's n minus x. Okay, so in this case, 6 minus 2. And the 4 plus the 2 must add up to 6. All right, and that gives us a 0,0595 probability. All right. Just a reminder, how you type that into your calculator, you're going to press your 6 button, then you're going to press shift, then you're going to press the NPR, and then you're going to press the 2. All right, and that'll give you the 6 choose 2. All right, and then 0,7 squared times 0,3 to the 4 gives you the 0,0595. So you can see here now we could work out now if she took 100 shots. All right, so if she took 100 shots and we want to see what is the probability of her scoring 60 of those shots, then we would say that the probability of x equaling 60 would be equal to 100 choose 60, and her probability of scoring will be to the power of 60, and therefore her probability of missing would be to the power of 40. Sorry, just check here. That should be NCR. Alright, sorry, not NPR. We're going to get to NPR. Alright, C for choose. Alright, so this 100 choose 60 times 0,7 to the 60 times 0,3 to the 40 gives us 0,00849. All right, let's look over the page. Okay, I'm not going to go through that. I just want you to take a bit of time. If you have to pause the video, do that. And look at the distribution graph for n equals 3 and n equals 6. All right, what I'm going to just highlight to you is notice how the graph is weighted to the right. Okay, because this probability of her scoring is higher than her not scoring. So the mean the mean is the expected values are going to be towards the middle. Okay, so the expected value we would say is maybe there somewhere, or here somewhere for that one. But wherever it is, if we had to work it out properly, it would be to the right of the median. All right. Just to go back to the first page. Okay, sorry, not the first page, but page 123 that had the tree diagram at the top. I just want to speak. I said I'm going to come back to these things in handwriting here. So we can either write 3 choose 3 like that, and we write it like that because we use the calculator button. But that means basically the factorial, 3 factorial over 3 factorial times 0 factorial. Okay, and that links to that in generic form. Okay, so it's n factorial is equal over r factorial times the n minus r factorial. Okay, so we'll deal with that a little bit more later, but you should remember that from last year. All right, back to page 127. All right, so as I said, it seems Thandi has higher chances of scoring more shots and less shots because obviously we've just discussed that the data is more popular or more weighted to the right-hand sides. But if we play around with the values of n and p, you can see how this changes the distributions. Okay, so now we're picking random variables here, but you don't need to worry about them or take anything down other than what we're filling in. This is just choosing random variables so that you can understand how it's weighted. Okay, so if we look still that there's 6 shots, n equals 6, but in this case we're going to bring down the probability of her scoring to 0.25%. Okay, 0.25, which is 25%. So that means she's less likely to score now than she is to not score. So in this case now, the data is weighted to the left, okay, or more popular to the left. All right, so looking at this one, what kind of probabilities do you think she's getting to score? All right, now it looks symmetrical. So in this case, there's still 6 shots because there's 6 different bars. And in this case, because it's symmetrical, the probability of her scoring is 0.5. Okay, then in the next one, you can't see all the values, but there are 50 shots, and her probability is still 50% because you can see the data is symmetrical. Okay, so looking at the first box, when she is a weaker player, that's with a 25% chance of scoring. When she has an even chance for the second box, or a 50% chance. And in the last one, she takes 50 chance. Okay, so what's important here is you must notice how this is starting to approximate a bell curve. Okay, a bell curve meaning that we've got a shape of a bell, or getting close to a shape of a bell. Okay, so we're not always going to be working out the entire distribution, and that's why example 1 was so long. The rest of the examples, the next 4, aren't going to be as long, and so we're going to look at more kind of examples that you'll get in tests and exams. Okay, example 2, a biased coin, remember, as opposed to a fair coin, is that there are more chances of it landing on one particular side than another side, and that's often used in magic tricks and illegal gambling, etc. And there are different ways that this can happen. It's either weighted more on one side, or sometimes the edge of one of the sides is more rounded, of the actual edge of the coin is more rounded than the other side, so that it's more likely to fall on that side. But that's not important. What's important is that how you work this out. Okay, so the probability of throwing a head is 2/3. Okay, so a 0.6 recurring chance of getting a head. All right, so A, what is the probability that exactly 5 heads appear? Right, so let's look at the solution. We're letting our random variable x equal the number of heads that show. Now let's look at the values or the information that we have. Okay, we're tossing the coin 8 times. So that means n equals 8. We know that the probability of our success, in this case, our success is heads because that's what they're telling us the probabilities are, is 2/3. And we need exactly 5 heads. All right, so using the formula, I'm going to write the formula so you get used to it. It is on your information sheet. That's n choose x times p to the x times 1 minus p to the n minus x. Remember, 1 minus p is q. All right, but it's easier to use p because then we only have one variable. All right, so in this case, we're looking for our random variable our success being 5 times out of the 8. So that's going to be 8 choose 5 times 2/3 to the power of 5 and 1/3, okay, because that's 1 minus p to the power of 3. And remember again that 5 and that 3 must add up to the 8, okay, the total amount of trials. All right, so you can put this onto the calculator, and that gives us a 0.2731, which is approximately a 27% chance. All right, let's look at B. The question is, now remember in A, it asked for the probability that exactly 5 heads appear. So in B, they're wanting to know that at least 2 heads appear. Okay, so if we want at least 2 heads to appear, that means that either 2, 3, 4, 5, 6, 7, or 8 heads could appear. All right? So in other words, what we're finding is the probability that our random variable x is greater than or equal to 2. But that would be quite difficult to work out, or long to work out, because we'd have to work out the probability of x equals 2, the probability of x equals 3, the probability of x equals 4, the probability of, and add them all together. Okay? So essentially, the probability of the random variable equal x plus random variable equal 1 plus the random variable x equals 2 plus all the way to the probability, sorry, let me redo that. The probability of our random variable 8, we know equals 1. Okay, the probabilities of all of them. So what that means is the probability that x is greater than or equal to 2 must be equal to 1 minus the probability of x equaling 0 plus the probability of our random variable x equaling 1. Okay, so it's much quicker to rather subtract the ones we don't want from 1, the full probability. Remember, all of these add up to 1. So it's much easier just to subtract these from 1 rather than to work out x equals 2, x equals 3, 4, 5, 6, 7, and 8 and working out those probabilities. You could do them, you'll get the same answer, but it takes much longer. Okay, so let's expand now on this step. All right, so we've got 1 minus. Now, the probability that x equals 0 means that out of 8 tosses of the coin, we are choosing 0, because 0 will be heads. Okay, times 2/3 to the power of 0 times 1/3 to the power of 8, because in this case, if no heads are shown, then all of them will be tails. And to that, we're adding the probability of getting 1 head out of the 8 trials. So that's 8 choose 1 times 2/3 to the power of 1 times 1/3 to the power of 7. Okay, because 7 plus 1 must equal 8. All right, so do this on your calculator and you get a 0.9974, which is approximately a 99.7% chance. Okay, much easier to work it out like that, subtracting it from 1, than to work out all the individual ones separately. However, if they'd said, what is the probability that at least 7 heads are shown? Then you'd only have to work out the probability of x equals 7 plus the probability of x equals 8. All right, then that would make more sense to do it that way, rather than saying 1 minus probability of x equals 0 plus x equals 1, x equals 2, 3, 4, 5, 6. That just becomes too long. All right, example 3, I'm going to go through these examples a little bit quicker, but obviously you can pause and go back if you need to hear something again. All right, so example 3, a fair die is thrown 15 times. A fair die meaning that the probabilities of those variables, of those numbers appearing are equal to each other. Okay, so on a dice there's 6 numbers, so each number has a 1 in 6 chance of being thrown. Okay, so let's look at A. What is the probability that 4 6s appear? All right, so we can go straight into it. We're looking at the probability of our random variable equaling 4. Right, so because there are 15 times we're throwing the dice, it's 15 choose 4. all right, times. Now the probability, they haven't given it to us, but because it's a fair dice, we know that it's 1 in 6. Okay, and we're looking at that happening 4 times, which means that the other 11 times out of the 15 is 5 over 6. Okay, so remember, this represents the probabilities of us throwing the 6 4 times. So that probability is 1 over 6. That will happen 4 times that we throw a 6. And out of the 15 times, the other 11 times then, it's a 5 over 6 chance that something else will appear, and that is not a 6. All right, so that gives us 0,14175, which is approximated to a 14.2% chance. Right, let's look at B. Okay, B is asking that less than 3 6s appear. So we're working out the probability that x is less than 3. Okay, which means that we're looking at the probability that x equals 0, in other words, that no 6s appear, plus the probability that 1 6 appears, plus the probability that 2 6s appear. Okay, 3 is not included, so we stop there. All right, so that is equal to, let's do the probability of x equals 0 first. Okay, let me rather use, I'm actually going to use color here. Okay, that looks a little bit better. All right, so the probability that x equals 0 will be out of the 15 times we're choosing 0. All right, and the probabilities now will be 0 for 1 over 6 because we're looking at it not showing a 6 at all, times 5 over 6 to the power of 15. Okay, so that's the probability that in 15 trials, none of them will be a 6. To that, we add the probability that out of 15, there'll be 1 head. So 15, choose 1. And now the probability of 1 over 6, or that a 6 is happening, is 1, times the probability of it not happening will now be 14. All right, and then lastly, the probability of x equaling 2 will be 15, choose 2. Then 1 over 6 will be to the power of 2, and 5 over 6 will be to the power of 13. All right, sum those probabilities up together, and you get a 0,5322, which is approximately a 53% chance. Okay, if you need to pause and take that down, you can pause now. Otherwise, I'm going to move on to C. Right, number C, what is the probability that 3 or more 6s appear? All right, so in this one, we're now looking for the probability that our random variable is greater than or equal to 3. Okay, which means that actually this would be x equals 3 plus the probability that x equals 4 plus all the way until the probability that x equals 15, which we clearly do not want to do. Okay, so we need to think of another way, because to work out, that's literally 12 different binomial rules that you'd have to work out and add. Okay, so we need to look at a different way. All right, so we know that the probabilities of all of them happening must equal 1. So in other words, the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. I'm not going to write them all the way until the probability that x equals 15 must equal 1. And this is why it's important, if you get to a question like this, to look at your previous answers. Okay, we have already worked out this. All right, we worked that out in B above. Okay, this represents the probability of x being less than 3. Okay, which we already worked out. Okay, the probability of x is less than 3. So this means that this the rest of them is the probability of x being greater than or equal to 3. Alright, so that means that the probability of x is less than 3 plus the probability of x being greater than or equal to 3 must equal 1. Okay, which means, that the probability of x being greater than or equal to 3 must equal 1 minus the probability of x being less than 3. Alright, and we already worked out the probability of x being less than 3 as 0,5322. So we can substitute that in, and therefore the probability of x being greater than or equal to 3 is 0,4678, which approximates to a 47% chance. Okay, just take note in questions how they ask you to round off, and stick to that. Here I know I haven't been consistent, but the questions haven't required it. Alright, if you need to pause and take down, now's your chance, and then I'm going to move on to example 4. Example 4. A bag contains 3 Smarties and 9 Jelly Tots. 7 items are randomly drawn one at a time from the bag with replacement. Okay, remember, with replacement is a condition immediately for binomial distribution. Okay, what is the probability that we draw 2 Smarties? Okay, so for the solution, before we answer this, it's important to make sure that this is binomial, okay, and it can easily be confused with hypergeometric, okay, and like it says, we're going to see that later. But why it can be confused with hypergeometric is that it doesn't look like there are only 2 options because there's 3 Smarties and 9 Jelly Tots. Okay? But the idea is that there are actually only 2 outcomes. Even though there's 12 sweets in the bag, you only have an option of either taking a Smartie or a Jelly Tot. Okay? So there are only 2 outcomes. Alright? And the 2 outcomes are a Smartie or a Jelly Tot. Alright, and secondly, as I've already said, there is replacement. Alright, so that means that it's looking like it's binomial. And also, we know that they're independent of one another, because if you take 7 items and you replace each one before you take the next one, the probabilities are going to be the same. Alright, they're also mutually exclusive because you can't take out a Smartie and a Jelly Tot at once. You're only taking one at a time. Alright, so it's either going to be a Smartie or a Jelly Tot, and there's nothing else that we can take out of the bag. Okay, so because of those, these probabilities are going to be binomial. Alright, so let's have a look at our values that we have. We know that n is equal to 7, because there's 7 trials. We have to take 7 sweets out one at a time, replacing them each time. And the question is, what is the probability that we draw 2 Smarties? That means that the Smarties are our success. So in other words, it's going to be the first of the 2 probabilities in your binomial formula after you've done your combination. All right? And therefore, we know that the probability of that happening will be 3 out of 12 because there are 3 Smarties out of the total 12 sweets. All right. So we are interested in drawing exactly 2 Smarties. So the word exactly implies that's when you're going to use an equals. When they say the probability of drawing 3 or more, or at least however many, that's when you're going to be using an inequality sign. All right, so the probability that x equals 2 is equal to, there are 7 trials, and we want 2 of them, so 7 choose 2, times the success probability, which is 3/12. That's to the power of 2 because we were looking at the success of drawing 2 Smarties, times the probability of drawing a Jelly Tot, which is now 9 over 15. Remember, the probabilities must add up to 1. So 9 over 12 is 1 minus 3/12. And that must be to the power of 5 because the 5 and the 2 must add up to 7. Another way of looking at it is that the 5 is the n minus x. Okay, in this case, the 7 minus 2. All right, work that out, and we get a 0,3115, which is approximated to a 31.2% chance of this happening. Okay, quite low because there are only 3 Smarties as opposed to 9 Jelly Tots. All right, this video has taken up almost a double, and that's without pausing. So if you have not finished this video in the lesson, then that is your homework. All right, over the weekend, by the time we get to your next AP lesson on Monday in class physically, you need to have finished this lesson. All right, and then what's going to happen in class is that your teacher, either myself or Mr. Borquin, will go through example 5 on page 130, which is a challenging one, so we'd rather do that in person with you, and then you'll get the exercise. Okay, so there's no homework as yet until Monday, other than making sure that you finish this video and taken down all the relevant notes. Thank you.